Hello everyone, and today we are coming to the next lecture about diamagnets and paramagnets. So in the previous lecture, we discussed what is the origin of magnetism, and we learned that it comes from electron, from its orbital motion as well as from its spin. Moreover, we introduced main physical parameters which we are going to use through the whole course. So today, diamagnets and paramagnets. I would like to start this part with this nice diagram. I took it from the book of Stansil and Prabhakar, a book on spin waves, and in the beginning where they discuss magnetism, basics of magnetism, they give this nice procedure how you can clarify with what type of magnetic material are you working. First question which you won't have to ask is if there are permanent magnetic moments in your material. If there are no, then you are dealing with diamagnet. If there are permanent magnetic moments, then you need to check if there is a long range order. So if your magnetic moments are somehow filling each other or they're completely independent. If there is no order, then it's paramagnet. If they are filling each other, then the next question is what is the orientation of neighbors? If they are parallel, then you're dealing with paramagnet. That's what we get used actually in our everyday life. Paramagnet is some magnetic material. But there is also a possibility when these magnetic moments will stay anti-parallel. And then the last question you have to ask is if the magnitude of anti-parallel moments is the same for both sublattices or it is different. So if sublattices have one which has this magnetic moments pointing in one direction and another sublattice has magnetic moments pointing in another direction, if their magnitudes are the same, then you're dealing with antiferromagnet. If the magnitudes are different, the magnetic moments of one sublattice is larger, for example, than this one, then this material is named paramagnet. Good, so this is the overview of the materials, and now I also would like to show you this picture from Krishnan, because as I said, if you want to find out what kind of magnetic material you have, first of all, you need to ask a question, what is its magnetic susceptibility? So it gives you the information about response of your body. Response means magnetic moment, which it will have when you apply some magnetic field H. And here on the left side, we are dealing with ideal superconductor. And as we know, when you will put superconductor within magnetic field, it will expel the field. Physically, you can explain it in a way that a superconductor has magnetization, which is equal minus applied field H. So M is equal minus H. And then immediately from this formula, you have the susceptibility of superconductor is -1. Good. Then when we move on, we are coming to diamagnets. So diamagnets, by the way, a superconductor, it's named as an ideal diamagnet, in the sense that its susceptibility, the absolute value of susceptibility is rather large. But important is that in both cases, susceptibility is negative. It means following: the diamagnets, first of all, it's not fully non-magnetic. There is some response of this material to the applied magnetic field, and this response is negative, meaning that your magnetic moments will be oriented in the opposite direction to the applied magnetic field. That's why it's negative. And next, what we have to see, that you see this response is very weak, 10 to the power -4. So it means the diamagnets are magnetic, but very weak. Afterwards, we are switching to antiferromagnets. And as we discussed, it's a case when they are kind of strongly magnetic, but you have these two sublattices, and magnetic response from one sublattice will be always compensated by the response of the second sublattice. Therefore, if you will check macroscopic parameters of antiferromagnet, it looks like completely non-magnetic, unless you will apply some huge field. But in the simplest case, you can say that antiferromagnet has zero susceptibility. So then we switch the sign of our susceptibility. So now we have positive chi. Positive means that if you have some magnetic moments and you apply magnetic field, these magnetic moments will be pointing in the same direction like applied field. And here we have paramagnets. So paramagnets have positive chi, and the value is not very large, so 10 to the power minus 2, which means that they are not strongly magnetic. At the same time, the magnetic response, let's say, up to 2 orders of magnitude more pronounced than for diamagnets. And finally, we are coming to ferromagnets. Ferromagnets, that's what we in our everyday life we get used to as simply magnet. And here you see that it's positive, but also its susceptibility can be more than 1. More than 1 means that your that your solid body can create fields on its own, that your total field will be larger than applied field H original. Okay, so that's it about the general classification of magnetic materials. Now I think we have a very nice overview and are ready to come to each of these types of magnetic materials a bit more in depth. And I would like to start with diamagnets. And here we are talking about so-called Langevin theory. First, what we need to keep in mind when we're talking about diamagnets, that in fact, every atom is diamagnetic, or it has some properties of diamagnets. Nevertheless, the point is that diamagnetism, this magnetic response, is weak compared to paramagnetism, ferromagnetism, and so on. Therefore, in most of the cases, if you have some paramagnetic response or something, you simply do not see diamagnetic contribution to it. And in this case, diamagnetism is simply ignored. Nevertheless, you keep in mind that diamagnetic susceptibility is in principle present in every atom, just small, and can be not visible. So where it comes from? Let us have a look first on this orbital. So this is our electron hydrogen model, so Bohr model of atom, which we discussed, and here is an electron which is flying around with some circular frequency and with some radius r. And as we discussed, the motion of this electron, since it's charged, will create a magnetic moment, orbital magnetic moment mu L, pointing in this direction. So it will create a current, as we were talking in the previous lectures. And here is the orbital momentum defined previously. So, and it's coupled also to the angular momentum of the orbital motion of electron. So, and the question now is what happens if you put this magnetic moment into external field H. As we know already, this magnetic moment will experience a torque, tau, which can be found simply as a cross product of a magnetic moment with a magnetic inductance B. By definition, torque also is a very temporal evolution of orbital momentum. And for us, it's important that now, instead of this orbital momentum, we can simply plug in this formula. And instead of inductance B, we plug in mu0h. Moreover, you see I have replaced them. So I exchanged mu and B with places. Therefore, we have no minus here. And this is done especially in order to be able to get this new parameter omega L, which is a vector. So this is a vector. Nevertheless, if you will take its absolute value and if you will divide it with 2 pi in order to switch from circular frequency to linear frequency, then this is nothing else as known to you Larmor frequency. So it means that this physics describes simply a Larmor precession, When you have magnetic moment of atom, you put it inside magnetic field, it will start to process. Frequency of precession is proportional to the applied magnetic field H. The next question you have to ask, what happens now, how this precession influences the magnetic response of our material. And this is very easy, because this precession will induce a new magnetic moment, which can be found like that. You can check all the steps in Krishna how it's derived. Here I just briefly explain you the main idea. And idea is that this formula is very similar to that one. You see, like we originally obtained the simplest orbital magnetic moment of electron. Now, instead of omega here, I put new omega, Larmor precession, this value. So now we are talking about new frequency, new circular frequency. And of course, we do not have any more this atomic orbital R, but we have a new value. But doing some summarization, so first of all, we need to understand that if you will consider now this precession, it creates a new loop of this current, and the diameter, the radius of this loop is not stable, so it will be changing in time, the process of precession. Nevertheless, you still can couple its average radio. You see, this means that we are talking about R squared averaged. You can couple to the original radius of precession of your electron, but you need here an additional factor of 3. That's why the magnetic moment created by the Larmor precession can be found in such form, where you have average R squared and divided over 6 ME, and is proportional to applied field H, because it creates a magnetic moment. And here it's a formula for the absolute value of new magnetic moment created by the Larmor precession. And the question is where it points. And here it's easy, because according to the Faraday law, the new magnetic moment which will be created by your atom will be pointed in such direction in order to partially compensate the applied magnetic field. So it means if your magnetic inductance is pointing in up, like it's shown in this figure, the new magnetic moment associated with the Larmor precession will be pointing in the opposite direction, like it's shown here. And this is the reason why the magnetic susceptibility of diamagnet is negative, because mu is trying to point in the opposite direction to the applied magnetic field. Then what we can do, having this magnetic moment for each atom, we can now calculate the diamagnetic susceptibility. In order to do so, you need first of all to find magnetization, M, and magnetization, you just need to summarize more or less all magnetic moments you have in your system. And that's why in this formula we see appearance of such parameters as atomic number, so how many electrons you have in your system, and also magnetization, it's total magnetic moment per volume. And therefore, we need also these two parameters, which is rho is a density and n0 is an Avogadro number. And H simply disappears because susceptibility is total magnetic moment divided by H. Therefore, H disappears, and here is your value for diamagnetic susceptibility. Good. To summarize, a few comments. First of all, usually people think about diamagnetic materials like about non-magnetic materials. It's not, strictly speaking, it's not correct, because we clearly see here that there is magnetic response of diamagnet to the applied magnetic field. Nevertheless, we keep in mind that this response is much smaller than other magnetic responses which you can have in the system. But second, what you need to keep in mind that this magnetic moment appears only after you applied magnetic field. So diamagnet is really absolutely non-magnetic as soon as you have no applied magnetic field. But if you have field, the application of the field creates this magnetic moment. And this magnetic moment is pointing in the opposite direction, trying to minimize it. That's why we have creation of magnetic moment with application of magnetic field. This magnetic moment is small and it's pointing in the direction opposite to the applied magnetic field. So these are the basics about diamagnets. And let us have a look which materials can be diamagnetic. Principally, of course, as I said, we want to avoid any uncompensated spin, for example, of electron, something like this. Therefore, first of all, we need to consider noble gases, like argon, for example, where all electron shells are fully filled. In this case, it means that orbital momentum is compensated and spin, so it means that you always have two spins pointing in opposite direction which compensate each other. So there is, it's very like neutral atoms and also neutral sense of magnetic response. And in this case, you can feel, you can see this small diamagnetic response of your atom. And that's why these gases are diamagnetic. Many metals, silver, gold, they are also diamagnetic, but here we need to be careful because to describe diamagnetism, to describe magnetic response of metals, you need different models. You need to operate with energy bands, and then some materials are diamagnetic, some are paramagnetic, and it's a bit more complicated to explain that, but just keep in mind that also copper is diamagnetic. Then we have semiconductors, silicon, gallium arsenide. They are diamagnetic. Molecules, H2, N2 are diamagnetics. And then also very interesting that water and our blood, so human being is also a diamagnet. What kind of interesting experiment you can do with diamagnet? And one of them is levitation. So since susceptibility for diamagnet is negative, high is negative, then magnetic moment, magnetization, will be pointing in the opposite direction to the applied magnetic field. But as we have seen, the potential energy of a magnetic moment placed within a magnetic field it can be found as a scalar product with minus. So, and now since you have here minus m, it's proportional to mb. It means that if you take your diamagnet and put it closer to your permanent magnet, namely increase in field magnetic inductance B, it means that you increase your potential energy. And system tries, of course, to minimize the potential energy. But in this case, what happens that your diamagnet is pushed away from strong magnetic field. Or if you want, you can find a force as a gradient of this potential energy. And if you consider only one direction, then you can get such a formula. And in this concrete configuration, it means that you will get some balance between gravitational force mg, which tries to put your piece of graphite, in this case, down, and force created by the magnet, which is pulling it up. And this experiment you can easily perform, or there are many experiments. You can find many different nice YouTube videos about superconductors. So if this is a superconductor, which is ideal diamagnet, and these are just some permanent magnets, it will be levitating. And by the way, there is this fast train, I think in Shanghai airport, which is really the whole levitating train, which can go very fast. And this is particularly the physical principle why it works. And now I would like to take a minute of break and just present you a brief story about the Ig Nobel Prize. So all of you know Nobel Prize, which is given for serious scientific achievements in different fields of science. And there is a so-called anti-Nobel Prize, Ig Nobel Prize, which is given for some strange and kind of useless achievement. And the philosophy, of course, is very good behind that. We need to laugh in order to think. So it's just a process which not only makes our life more interesting, but also stimulates the way of thinking. And as a good proof for this is a story with Dr. Andrew Game, who got a Ig Nobel Prize in 2000 for levitating frog, which you will see in a minute. But 10 years later, he got a real Nobel Prize for the discovery of graphene. So it's a nice story. And here is the movie I would like to show you. But before, I want to show you briefly another movie which shows that we are really surrounded by diamagnetic materials. Okay, let us have a look.
Okay, hey everybody. Today I'm going to show you how everything is magnetic. So I have my super strong neodymium magnet.
These magnets will crush your fingers.
They're very strong. I have 2 of them. Notice I have this one clear over here. So I just typically keep them in my kitchen mitts because if they get stuck together, they're not coming apart again. So what I'm going to show you today is how everything is magnetic. So we all know that yes, a magnet can attract another magnet, but what you might not have known is that everything is magnetic. Water, air, people, wood. So I'll show you these effects of diamagnetism. Everything repels a magnet. I'll show you that. What I have here is a syringe full of water and I have my strong magnet. I'm not going to touch the magnet too, I'm just going to bring it close and the water is going to repel the magnet and get pushed.
Kind of looks like you're touching it.
Not touching it.
Prove it. Oh, there you go.
Let's push it back. Not touching it.
So we can clearly see that water is diamagnetic.
So water repels a magnet. Another thing that repels a magnet is wood. So here's an ordinary block of wood. I'm going to bring the magnet close to it but not touch it.
Let's change that angle.
Okay. See how it's not touching it, pushing it away. Can't really see.
It's stopping it.
Let's push it away.
So how is it doing this?
So diamagnetism is a quantum mechanical effect which I won't get into, but essentially it's repelling the magnetic field.
So principally we can move on. You have seen the experiments and you got already the understanding why it is diamagnetic and why it is pushed away from applied magnetic field. And I'm switching to the next experiment. In order to perform this experiment, you need superconducting magnets in order to create a huge, very large magnetic field. That's why you've seen liquid nitrogen.
Which is beyond. If you have a look here, this is.
And this is this little frog. And now camera is showing you the magnet. And you can see that frog is levitating. It's alive, it doesn't feel any hurt or something. Maybe a little discomfort. But it's a nice experiment which proves that alive beings are diamagnetic. So if you will find a way to create large enough magnetic field, you can also levitate as a frog. And now I would like to switch to paramagnets. As opposite to diamagnets, paramagnet is a material in which magnetic moments are present all the time even if you have no applied magnetic field. Usually these magnetic moments are depicted with such arrows, and in the case of absent magnetic field, they usually point in all possible directions. So they are independent, and temperature kBT brings a chaos into the system, and they simply change their orientation in all possible ways. That's why all possible directions. That is why when you will try to find magnetization of paramagnetic material, and you summarize magnetic moments for all possible you will try to find macroscopic response, magnetic response from all magnetic moments. So this is a magnetization. It's vector sum of all magnetic moments divided with the volume of your body. You will get 0 here. So it means that for each magnetic moment which is pointing in one direction, there will be another one pointing in the opposite direction, which compensates its response. Next question is what happens if we apply some magnetic field. You see that usually in this case you still have chaos, but if you will look more carefully, you see that now more arrows are tending to point along the applied field and less arrows are pointing in the opposite direction. So it means that you still have this chaos, but already some visibility of order shows up here, since most of them, say, try to point more along this direction. And as a result, your magnetization, in this case, the total magnetic moment will not be 0 anymore. It will be small, but not 0. And M will be pointing along the applied magnetic field M. Therefore, we can speak about positive magnetic susceptibility. In principle, theoretically, you can reach a third case if you will apply a huge magnetic field. So 1 Tesla, it's a field created on a surface, for example, by this neodymium magnet shown by the guy in the video. Or maybe, but you probably would need a bit larger magnet for that. And let us check what should be the field that we can orient all magnetic moments along to have fully saturated state at room temperature. For this, we need to compare two energies. First of all, magnetic energy, and let's have a look what will be magnetic energy for this rather large 1 Tesla field. For magnetic moment, we simply take a magneton Bohr for simplicity. And then our energy, you can make the simplest calculations, will be 9 × 10⁻⁻24 joule. Let us compare it to the thermal energy. Thermal energy is easy, so we are speaking about room temperature, 300 Kelvin, kBT. We will get the value 4⁻⁻21 joule, which is around 3 orders of magnitude larger than magnetic energy. So it means even applying such a large field, you will not get a magnetic order as it is shown in this picture. If you want to get order in the system, one needs to apply fields of order of 1000 Tesla, which at least in static regime is not possible to achieve to the best of my knowledge. At least in labs, usually people work with fields smaller than 50 Tesla. And of course, you can decrease temperature, and then you can get saturated state for paramagnets, but it's hard to do it for room temperature. Okay, and now I would like to make a little detour and to focus on lanthanides metal. So this is periodic table of elements, and lanthanides are shown here. And these are materials, and you see that some of them are paramagnetic, some of them show antiferromagnetic behavior at very low temperature. Gadolinium can show also paramagnetic behavior. But usually, so you can, for example, europium, it will be paramagnetic, and let us have a look closer to it. First of all, we need to have a look at the atomic structure of europium. So it's an element with atomic number 63. So it means that it has 63 protons, nuclei, and 63 electrons. Its atomic weight is around 152. So it means that in addition, you have 89 neutrons in its nuclei. And in this picture, you see the shell structure and electronic configuration of the atoms. So we are coming in a minute to this. And also here are these nice 3D pictures of different SPD shells, how they're looking. Okay, and the first question you want to ask is, okay, I have so many energetical levels given by principal quantum number n defined, and how do I feel them? And if you go to the inner shells, then it's easy. You just first fill S1s shells and 2s, 2p's, and 3s, and so on. But starting from some point, you will not be able to fill simply fully one shell and then switch to next principal quantum number. The system is getting more complicated, and here you're talking about so-called Modelung or energy ordering rule, which tells us that electrons are assigned to orbitals in order of increasing value of n plus L, so plus orbital quantum number. And it looks as following. So you first need shell S, then 2s, 2p, 3s, 3p. Then instead of going to 3D, you are going to 4s, you're jumping back to 3D, and then the shells are filled in such a way. And that's exactly what you see also if you will plot energy. So here on this axis is energy, and you can see that first energy increases, but then you have, after 3p, you have 4s energy, and then 3d energy. So on afterwards, this level will be filled, then 4p. Then you jump into 5s, 5p, then coming back to 4d. Therefore, it's a question how you need just to keep in mind how you fill your energetical levels, because it's related to the question of ionization. And when we are talking about magnetic properties of lanthanides, we usually talking about ions, 3+. So it means that out of your atomic structure, you need to remove 3 electrons. So ionization is another question, but the general idea behind that you first of all will remove that electrons which are weakest coupled to the nucleus, and it means the distance is important. So usually the outer shell will be removed first because Coulomb interaction is weakest, but also you need to take into account shielding of your electron by other orbitals. So if you have negatively charged, positively charged, but here you have a shell which is also negatively charged, it also decreases that interaction between nucleus and your electron. And if to speak about the ionization of europium, for example, then what happens is these 2 electrons are removed, and then afterwards you start to remove electrons from 4f shell, while 5s and 5p are staying the same. Good. Now, again, I would like to make a little refreshing of your memories about the how these electrons now fill each the electronic shell, because as you know, electrons can have spin up and down, and it can have different quantum numbers ml, and the question what will be filled first. And the answer is given to us by the empiric Hund's rule, which tells us that first of all, we are filling our orbitals in a way that as the total spin angular momentum will be maximal. So it means that if you have here 1, 2, 3, 4, 5, 6, 7 slots, and in each of them you can put 2 electrons, what happens then, you first of all will start to put electrons one by one with the same spin orientation, like it's shown here. Then second rule tells us that we will have to maximize the orbital angular momentum quantum number L, like it's shown here. And What does it mean? It means that you start putting electrons here from +3, +2, +1, and so on. So you fill electrons again in such a configuration. And only after your shell is half filled, you are starting to put new electrons with opposite spin direction. And again, you start with a positive larger value of ml and go on. Then the last rule of Hund gives us information how to search for a total angular momentum. And if your shell is less than half full, then it will be a difference between orbital and spin momentum. If your shell is more than equal to half or more than half full, then you will get here a sum. So you need to, your total angular momentum, J will be equal as L plus S. And here you see this scheme which is used for the definition of all these atoms and ions, like shown here. Okay, so that was it about the basics of atom physics. So now we know why our electrons are sitting in these shells as they are sitting. And the question is why these rare earth ions are so interesting for magnetism. And the answer you can see here. The point is that all outermost electron shells of these electrons, 5s2 and 5p6, which have around 1 angstrom radius, are identical. So you jump from one electron to another and these shells are the same. And then chemical properties and crystallographic structure and so on are defined mainly by this shell. The response, magnetic response as opposite, is given by the 4f electrons, which are sitting in the inner shell, here with a radius, for example, 0.3 angstrom. And then we have a very unique situation that even if you have not an ensemble of individual atoms, which you practically never can have in reality, in nature, you have a complex solid body with many different processes which should be taken and different interactions which should be taken into account, you still are able to describe magnetic response of this material simply analyzing these 4f electrons, simply analyzing your solid body as an ensemble of non-interacting ions. And for example, in this book of Gross-Marx and Kittel, you can find nice tables where the magnetic moment of each atom is calculated theoretically and compared to experimental value. And you will be surprised that in spite of all complexity of the system, the simplest atomic atom physics model describes magnetic response very precisely. So that's it about rare earth ions. And we are moving back to the question, okay, and how to get the susceptibility of paramagnetic materials. And here we again are talking about Langevin theory of paramagnetism. And in this theory, we need to consider an ensemble of independent magnetic moments, M. And what we do exactly like we have seen in the slide with these green arrows, we need to put them into external magnetic field. And then each of the magnetic moments will experience a change in its potential energy, which can be found like this. Then what you do, you just use standard classical Boltzmann statistics, which is found like this: potential energy divided with kBT, so Boltzmann constant time, temperature. So this is thermal energy of your system. And then you would have to do few mathematical steps, which you can read here in Krishnan. But here I will just give you the final result with only comment that at some point you would have to use the approximations of this formula shown here works for large fields H of a small temperatures T. So the proper formula looks slightly more complex, but this one is the most famous and it's known as Curie law. And its physical meaning is very simple and clear, that paramagnetic susceptibility is simply inversely proportional to the temperature, where this constant C, it depends on this constant mu0, density of magnetic moments, magnetic moment itself squared and divided with 3 kBt. So this is such a constant which describes your body, your material more or less. But what's important physically here is that susceptibility is inversely proportional to temperature, and this you can easily understand that the higher temperature is the larger chaos you bring into the system, and it's harder to position your magnetic moments in the same direction. With decrease in temperature, your susceptibility grows because you don't need to apply so large field in order to get magnetic order. Yeah, so just a few words. We will not discuss in this lecture superparamagnetism, but in some cases, you should not necessarily consider this M magnetic moment as a single atom magnetic moments or ion. Instead, you can work with some clusters of magnetization, and then you will get more or less the same physics, with the difference that magnetic moments of each this single independent magnetic moment will have many orders of magnitude larger magnetization. And then you can again get in the same way the susceptibility of superparamagnetism. Good, and now we would like to switch a gear and to give you some practical experiment, really great one from YouTube, but I need to say a few words before we will watch it. In this video, the molecules of nitrogen are compared with the magnetic behavior of nitrogen. Liquid nitrogen is compared to the magnetic response with liquid oxygen. And here we're talking not anymore about atoms, but we're talking about molecules and two. And if you will look on the atomic structure of nitrogen, you will have 3 electrons sitting in this 2p shell. And as we know from Hund's rule, they will be located like this. Now, when you bring that into molecule, you will get here this generation of new 4 energy states, which you are filling with 6 electrons, like shown here, yeah? 6. And in this case, what you can see is that here, magnetic moments from spins of these electrons are compensated. So here you have completely filled shell. That means that molecule of nitrogen is diamagnetic. Now let's have a look what is with oxygen. Oxygen has a very similar atomic structure with the difference that here we have 2p4 instead of 2p3. It means that electronically you have here 1 extra electron and 1 extra electron here. And then when you form a oxygen molecule, these 2 electrons will go up, and according to the Hund's rule, they will have the same spin. So it means that you have here uncompensated spin, you have related magnetic moment, and it brings you to the statement that molecule of oxygen is paramagnetic rather than diamagnetic. And what's also good for this experiment, the boiling temperature of oxygen is 90 Kelvin and of nitrogen 77. So it means that liquid nitrogen temperature is sufficient to bring your oxygen into the liquid state. And that's why we will have a look now. And let's have a look now on the experiment.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
This is our liquid oxygen. So this is nitrogen, which is diamagnetic. Have a look how it behaves when you put it through magnetic field. It either doesn't feel it or maybe even slightly pushes away from the field, or from the poles of magnet. And now let's have a look on paramagnet behavior. It's really magnetic, yeah? But it's trying to stick to the poles of the permanent magnet. Good, I think this video is really great to feel the difference between these two behavior, and it finishes a part about diamagnets and paramagnets, and in the next lecture we are coming to ferro, antiferro and ferri magnets.